Okay, so deletion of a node, it should not affect the BST. Okay, any node if I want to delete, it should not affect that BST. Okay, that means BST property of other nodes, it should not be changed. Yeah. So what are the different cases? If I have to delete a node, first of all I have to search that node. Okay, I have to search that node, and we have seen the search algorithm, recursive as well as iterative. So by using any of those methods, we can search the particular node, and then we will check what type of node it is. Okay, so suppose I want to delete 23, I will be searching first 23 here, and I found it at this position. And deletion of this 23, it will affect the left subtree as well as right subtree and the parent. Isn't it? It has 3 links, one link coming from the parent. So 17 should have another right child, isn't it? In order to continue the subtrees, it should have the proper right subtree after deletion of 23 also. And this 23, deletion of 23, it should not affect that. I will be having the path to reach to these nodes in the left subtree of 23 as well as right node of 23. Okay, and it should be BST only. So after deletion of 23, it will affect the outgoing links, these left right child links, as well as the incoming link, that is the link from 17. Okay, so I have to see what should I do for this. Okay, which should be the next node which will be replacing this 23. Okay, or which should be the root of this right subtree, because 23 is the root of the right subtree of 17. So I should find a node which will take place of that right subtree root. Okay, so this is the node to be deleted. So there are 3 conditions. If I have to delete any node, there will be 3 cases. That node can be a terminal node, that is a leaf node. So if it is a leaf node, then it will not have any subtrees. And if I delete that node directly, it will just modify the link coming from the parent, that single link coming from the parent. Okay, so that is the case of terminal node. Then the node which we have to delete, it might have only one child, and the second child will be null. Okay, so it is a node with one child, or it can be a node with 2 children, like we have seen now, the 23 node, that is the node with 2 children. Okay, so these are the 3 cases for the node to be deleted. And when we search a node, we have to also see what type of node it is. After that node is found, we have to see what type of node it is, whether it is a terminal node, whether it is a node with single child, or it is a node with 2 children. And in all these 3 cases, we have to have different logic for deletion. Okay, so we'll discuss one by one condition. Suppose in this BST, I have to delete node 8. Okay, I have to delete node 8. So I will start searching from root. 8 is less than 10, so will go to the left subtree. It is greater than 4, we'll go to the right subtree. It is less than 9, we will go to the left, and it is greater than 7, so we'll go to right. And we found 8 here. The node to be deleted is present here. Now, if I delete this node, it does not have any left and right children. It has only one link coming from the parent. So when I reach to this 8, I will also hold the reference of the parent node, like we have done in the insert function. Insert iterative function, we did this. We had kept reference of parent node, and then we moved current. Okay, so when I'm finding this node 8, okay, that means my current has reached from root to this node 8, and at the same time I have modified my parent. Okay, so before I move current to 4, I will keep reference of parent in a variable. Okay, suppose parent variable. Then when I moved current to 9, I have kept reference of 4 in parent. When I moved current to 7, 9 will be parent. When I moved current to 8, 7 is in the parent. And when my current matches to the required data, okay, current matches to the required data, this current is to be deleted. And I have a link to the parent. Okay, and I know that current is attached to the parent right because it is greater than parent. Okay, so I can easily say that parent right is equal to null, so that this link will be broken. Okay, when I say parent right equal to null, this link will be broken, and we will have the modified BST. Okay, and then when if we traverse this BST after deletion of this 8 also, if we traverse this tree, we will see that it is a BST only. Okay, so deletion of 8 has not hampered this BST. Is it clear? Deletion of leaf node, even if it is the left child, suppose I have to delete this too, this is also a leaf node. Okay, and this is current, and 4 is the parent. So we can easily say parent left is equal to null. Instead of pointing to 2, it will point to null, so that this link will be broken. And the resultant BST, remaining BST, it is BST again. It is satisfying the BST properties. Okay. Clear? Deletion of the terminal node, that condition. Which Bhavesh, you are talking about which figure? I'll just check. 10, 24, 9, 7, 8. What is wrong here? Are you saying this figure is wrong? 69. Okay, I'll check. Seventeen 23 1 17 20. Yes, this 17 should not be here. Correct. This is actually from the book. In book only it is wrong. Instead of 17, consider it as 27. Okay. Yes, correct, Bhavesh. This 17 should not be there. It should be something greater, maximum number. So we can say it is 27. Okay. Yeah. Yes, good. Fine. So deletion of the terminal node, that condition is clear. We'll read about it. If the node being deleted is a terminal node, then deletion is a straightforward procedure of just making the parent node point to null. Clear? This is the first condition. Then the next condition is the node being deleted, it has one child. Okay, the node being deleted, it has one child. That is the node similar to 9 or similar to 7. If we want to delete a node like 9 or 7, which has one child and another child is pointing to null, then what will happen? Suppose I have to delete here 9. Okay, I have to delete here 9. So there are two links attached now. One is the link going to this child, and one is the link which is coming from this parent. And I want 4 to be pointing to the new root of this subtree. Okay, because 9 is the root of the subtree currently, and as I want to delete 9, another node should replace this 9. Okay, that means 4 should directly point to the child node. Right? So if I say this parent right is equal to current left, parent right is equal to current left, then it will be modifying the root. Okay, this deletion will not affect our BST if we check the in-order traversal. Okay, and this link is as it is. So 7, this subtree, complete subtree will be shifted here. Okay, so 4 right, instead of pointing to 9, it will point to this 7. Okay, which is greater than 4. And 7 right is 8, which is greater than 7 again. So that will be the BST. Okay, so there are 4 subconditions in this case. That I will just draw here another this sub diagram. There are 4 subconditions of this particular case. One is parent is having this current as a right child. Okay, parent is having this current which is to be deleted as a right child, and the node which is being deleted, it is to the left. This condition we have seen just now. Instead of left, suppose this node, this sub node is attached to the right. Okay, don't see the values at this moment. Okay, don't see the values at this moment. We will just concentrate on the cases. Okay, suppose this is the subtree from which we have to delete this 9. Now, which is this case? Current is having right child and current is attached to the right of the parent. Okay, current is having right child and it is attached to the right of the parent. Then here, if I have to delete this current, the parent right, it should directly point to current right. Okay, parent right should directly point to current right. Fine. And another condition which we saw was this one, where the current is attached to the right of the parent and the current is having left child. This is one more subcondition. Similarly, reverse of this subcondition is current is attached to the left of the parent and it is having left child. This is another subcondition, third subcondition. Okay. So it is like, suppose we have a left child to 2, which is 1. Okay, that can be the subcondition which we are looking after. Okay, so if we want to delete 2 in this case, then that is the subcondition which we are looking after. That parent is having current as left child and current is having left child. Okay, so in this case, if we want to delete 2, that is the third subcase. And fourth subcase is if we have current is the left child of the parent and it is having right child. Okay, current is the left child of the parent and it is having right child. So this subcase, which if we want to delete 7 from here, 7 is attached to the parent as left child and it is having right child. So in this case, what transformation will be done if we have to delete 7? Then parent left is current right. Okay, in this case, parent left is current right. In this case, if we want to delete 2, parent left is equal to current left. Okay, that will be the transformation. So that this link parent left, it will directly point to 1. 4 left will directly point to 1. And these two links will not be there. We will say current left is null and delete 2, delete current, like that. Okay, so that will be another subcondition. So there are 4 subconditions. Okay, 4 subconditions of this second case, deleting node having one child. So we have to check first whether that current is the node with the single child, that is having left child or right child, and we also have to check whether this current is attached to the left of the parent or right of the parent. And depending on that, we have to do what we have to write what transformations we will be making. Okay, so whether this type of scenario is there, or this type of scenario is there, or this one, or this one, you have to check what type of scenario is getting followed for this node with single child, and accordingly you have to do the transformation. Is it clear? Node with single child, that condition. Any doubt? So we have seen 2 subconditions. One is node with no child, that is leaf node. Then second is we have to delete a node with one child, which has 4 subcases in it. Okay, are you getting any doubt in this, in these 2 conditions? If you have, please ask. So we'll go through it. If the node being deleted has only one child, then the parent node will have to point to the child node of the node being deleted. Okay, so we have to point to the child directly. That parent will be pointing to the child directly instead of pointing the current node which is being deleted, and then we will be able to delete that node. Clear? 2 conditions are clear. You have to write the code for this, all these conditions, remember. And the third case is the node being deleted is node with 2 children. Okay, in that case, suppose in this tree we have to delete this 23. Okay, node being deleted is node with 2 children. Then can we directly make this element as the root of this subtree? Can we directly replace 21 here as a root, or no? Then where will this child go? Right child. Okay, so we cannot directly replace because this is also having the children. Okay. In this case, suppose we have to delete the node 4, which is having 2 children, 2 and 9. Then after deletion of this node, this should be the BST only. So there are 2 nodes which can replace this particular node. Either the lowest node from the right subtree or greatest node or largest node from the left subtree. Okay, only these 2 will be able to replace that particular node. The largest node from the left subtree or the smallest node in the right subtree. Clear? Where that largest node in the left subtree is present, it is present to the rightmost of that left subtree. Okay, and the minimum in the right subtree, it is present at the leftmost of that subtree. Isn't it? We have seen where is the minimum present in the BST and where is the maximum present, and that is true for the subtree also. And that element will be able to replace this particular node. Are you getting? So in this case also, if you have to delete 23, either the largest node from the left subtree, which is present at the rightmost, this is this 22, it will be able to replace this 23, or imagine this is 27, not 70. Okay, so in the right subtree, the smallest node, it is present at the leftmost of the right subtree. Okay, so that will be able to replace it. Consider another node also. Suppose I have to delete this 17, the root. Then who will be able to replace it? Either the highest in the left subtree, that is 11, or the lowest in the right subtree, which is present at the leftmost of the right subtree, which is 20. Okay, these two nodes will be able to replace this 17, 11 or 20. Okay, which are present. If you write the in order traversal, then this is present to the uh, left of the 17, and this is present to the right of the 17. So any of these two will be able to replace this node. And if they are replacing, if 11 is replacing suppose 70, suppose we are selecting the this node 11, it is also called as the predecessor of 70, and 20 is called as successor, in order successor. 11 is in order predecessor. Okay, so if we select in order predecessor to replace the node, then you have to find first this in order predecessor, and then that value will be copied here. So 11 will get copied here, and then we will delete 11. We have already seen the condition to delete this 11. It can be a leaf, or it can be the node with single child. Okay, the predecessor will never be node with two children. Clear? In this case, both of them, 11 and 20, are the leaf nodes, and we have seen how to delete the leaf nodes. So we will be copying the value of 11 here and deleting 11. This node will be deleted. If we are selecting a successor, in order successor to replace this, then we will be deleting 20 by after copying 20, the value 20 here in this 17 node. Okay, so 17 will be replaced by 20, and then 20 will be deleted. This node will be deleted. In this example also, if we want to delete 4 from the right subtree, the leftmost, that is this 7, will be replacing 4. Okay, in order successor of 4 is 7. So 7 will be replacing 4, and we have to delete 7. And we have seen the condition to delete a node with single child, isn't it? So 7 will be deleted accordingly. So 9 left will be 8. In this way. Okay, if we have to delete 10, then we can find in order successor or predecessor. So if we select in order predecessor, 8 will be replacing 10, and we will be deleting 8. If we select in order successor, then 20 will replace 10, and 20 will get deleted. And we have seen conditions to delete the leaf node. Okay. So the third condition is deletion of a node with two children. If the node being deleted has both the children, then we first need to find the in order successor of that node, or in order predecessor, whatever you will select, but stick to the same logic. Okay, for deleting every node with two children. Find the in order successor of the node being deleted and replace the node being deleted with this node, and you have to delete that node. Okay, that successor node will be deleted. The in order successor of a node can be obtained by taking the right node of the current node and traversing in the left till we reach to the leftmost node. Okay, so right in the right subtree, leftmost will be the in order successor. Okay. So for deleting terminal node 8, we will search the parent of 8, which is 7, and make right of 7 null. Okay, in order to delete 8. Then deletion of node having one child, that is delete 7. If we have to delete this 7, then 8 becomes left of 9. 8 will become left of 9. Okay. Then the third case is deletion of the node with both the children, that is 4. Then in order successor of 4 is 7. In order successor of 4 is 7. So replace 4 with 7, but this affects the node 9 and 8. Attach 8 to the left of 9. Okay, the condition which we have seen to delete the single child. Is the deletion logic clear? What is predecessor and successor? Predecessor is when you traverse in order. Okay, suppose you traverse this tree in order way. Then in the in order traversal, here we will start with 1, then 2, then 4, 7, 8, 9, 10, 20. This is the in order traversal. And in that in order traversal, who is before 4, that is the predecessor. And the node which is after 4, it is successor. Okay. Deletion of node with 2 children. Okay, I'll do that. So in this case, suppose we have to delete 4. This is the node with 2 children. Okay, it has 2 children. So I cannot delete this 4 directly because it will hamper the left subtree as well as right subtree. And who will be able to replace this node 4? Either the in order successor, which is present at the leftmost of right subtree. This is the right subtree, isn't it, with these 3 nodes. In that, the leftmost node, that is this 7. Or we can find in order predecessor, which is present at the rightmost in the left subtree. So in this left subtree, the rightmost node is 2 only, because 2 is not having again the right child. If there is 3 present to the right of 2, that will be the in order predecessor. Okay, so 2 itself is the in order predecessor. So you can select 2 or 7, in order predecessor or in order successor. So in my case, I am selecting in order successor, and that successor node will replace this node to be deleted. So instead of 4, there will be 7. 4 will be replaced by 7, and we will delete 8. We will delete 7. And we have seen the condition to delete 7. Because 7 is the node with single child. We have seen how it will be deleted. Okay. So in order to delete it, we have to say 9 left is equal to 7 right. It is parent left is equal to current right. So here we will directly have 8, and this 7 will be deleted in this way. Isn't it? Are you getting how the deletion happened? 7 replaced this. 7 is the in order successor of 4, so it replaced 4. And then we deleted 7 from here, from the right subtree. Okay. Okay, thank you. The case for 10. Okay. Suppose we have to delete this 10. Then in order successor of 10 is 20.
Ma'am, got it.
Got? Okay, fine. No problem. So we have seen all the functions related to BST. The insert, then searching, recursive, non-recursive, then we have discussed deletion, and also some of these functions we have discussed. Height, recursive we have discussed, mirror, finding leaf nodes, copy, compare, minimum and maximum in BST. Okay, so write maximum of these functions in your second assignment. Try to implement all the functions. Okay. With this, we have completed the BST. And we'll start with the next part, which is threaded binary tree. Any doubt up to now? We have discussed binary tree in detail. Then we have discussed binary search tree in depth. Okay. If you have any doubt in this, you can ask. Otherwise, we will move. Okay. The next part of our unit 1 is threaded binary tree. So, can you tell what will be the meaning of thread? What exactly is a thread? Yes, anything that you can imagine? What will be this thread? No prediction? Okay. We have seen tree traversal algorithms and we have implemented also, isn't it? In order, pre-order, post-order traversal. Then we have also seen the level-wise traversing using queue. In the in order, pre-order, and post-order, we have also seen the non-recursive methods where we have implemented our own stack and used the object of that stack for traversal purpose, isn't it? Now, what is the drawback of those traversals? Whether it is recursive or non-recursive. Can you tell? Are there any drawbacks of these traversals? Please respond. Can you think of any drawback of these traversal methods? Yes, anyone? Sequential flow of elements can be considered as thread. No, Ria. One direction flow. Okay, we'll discuss what exactly is thread. Before going to that, we want to find out whether there is any drawback of the traversal methods which we have discussed or which we have used. Is there any drawback of those traversal methods? Time consuming. Why it is time consuming? Why is it time consuming? Traversing. Time lapse during recursion. Okay. So, in both these cases, whether it is recursive or iterative traversal, we use stack. Okay. In case of recursive traversals, the implicit stack is used where the status of the pending calls is stored. And in case of iterative traversal, we use our own stack object. So we need extra memory for the traversal purpose, isn't it? Even if we use the level-wise traversal, then also we need to use queue data structure. So we need extra memory for traversal. Okay. So that is the disadvantage of the traversal methods we saw. And one more thing is, if you I'll go to the previous slide again and tell me how many uh, for this particular tree which I'm showing you. Okay, for this tree, how many nodes are there in this tree? Can you count? Yes, how many nodes are there? 8. Good. And how many null pointers are there? How many null pointers are there? Can you check? Which are not shown here, but you can always see 20 left, right, it is having nulls. Okay, so these are 2 null nodes. Then this one is 3, 2 right. Then 4, 5, 6, 7, 8, 9. Isn't it? 9 null pointers, isn't it? Even if we are not showing here. But there will be 9 null pointers. For 8 nodes, 9 null pointers are there. Can you count? Yes, correct. So whatever actual data is present, more than that, we are having null. Okay, so we are wasting the memory. We are wasting the memory in storing null nodes. Okay, and if we want to utilize that memory of null nodes in the proper way, then threaded binary tree is the way for that. Here in threaded binary tree, we are using that null memory for traversal purpose. So both of our things are getting utilized properly. Okay, null nodes are used for traversal purpose, and we don't need the extra memory also, like stack and queue for traversal. Okay, so in tree traversal, we have seen recursive methods which are inefficient if the tree is to be traversed frequently. So as Ria said, if the tree is to be traversed frequently, these recursive methods are inefficient. Okay, because multiple times push pop will get accessed in order to store the status of the pending calls or retrieve the status of the pending calls. Then backtracking using stack, where we used our own stack object, it is slow and inefficient. Okay, so these are the disadvantages of the tree traversal methods which we have seen, and that's why there was we can say need or invention for this threaded binary tree by these two scientists, Perlis and Thornton. So what they thought of as binary tree have a lot of vested space. The leaf nodes each have 2 null pointers. We can use these pointers to help us in in-order traversals. Okay, so we can use the null pointers for traversal purpose. In a linked representation of binary tree, there are more null links than actual pointers, that we have also seen by counting. If there are n nodes, link representation have n plus 1 null links. Okay, these null links can be replaced by pointers called threads to other nodes. Okay, so these threads are nothing but pointers. Okay, these threads are also pointers. Got the basic idea? We'll see what is the structure of threaded binary tree or how it is useful like that. So we have the pointers reference the next node in the in order traversal called threads. Okay, So what are these threads? These will be the same null pointers which will be utilized to point the in-order successor. Okay, so as the in-order successor will be pointed by the thread, no need of stack to store the parent, because we can use that thread to traverse the next node in the traversal. Okay, using thread. A left null link of a node is replaced with the address of its in-order predecessor. Okay, if the null is present to hello, hello. Uh, there is no power now, so I'll share the attendance link, but we'll continue with this TBT in the next session. Okay, we have to implement the threaded binary tree also. That is our third assignment. Attendance link is shared. We'll continue with the TBT concept in the next session. Okay, thank you. But implement the BST in the